Hey everyone and welcome back. Over here we are starting with a new topic which is recursion. Now I have placed recursion right at the beginning part of this course because recursion is a very important topic for any coding interview. You will see that as you go on with this course that recursion is in fact the parent of various other topics such as backtracking, dynamic programming, greedy algorithms, divide and conquer algorithms, etc. Now more of that later in the course. Over here, let's try to spend some time and understand recursion thoroughly, and then let's go ahead and take a look at a few interesting coding interview questions. So let's get started. Now these are the topics that we will be discussing over here to understand recursion thoroughly. So let's get started. The first question over here is, what is recursion? Now, in simple terms, recursion is just a function calling itself until a base condition or a terminating condition occurs. Let's take an example to understand what is written over here. Let's say you want to print the numbers from 1 to 5. And if we were to write the pseudocode for this, one way of course to do this would be by having 5 print statements. But of course, this is not an optimal way for various reasons. For example, what if instead of 5 you have 100 over here? And even worse, what if you don't know this and if it's just a variable? So we know that this is not an optimal approach. Another approach to handle this would be to use recursion. Now, if we were to write the pseudocode for this, it would look like this. You have a function, you can name it as you want. I've not given it any name over here, and you have the body of the function over here, and you call the function over here with a particular input. In this case, we are calling the function with 1. Now, when you come over here, when the control comes to the function over here, n is equal to 1, and then inside you have a statement over here, if n greater than 5 return, but n is 1, so you don't execute this. You come over here and you print n. So n over here is 1, so you print 1, and then notice over here that inside the body of the function, you're calling the function again recursively. So that's what is function calling itself. So over here, we're calling the function again with a different input, and again you will see that many times it's about making the input smaller, or a better way of saying that would be making the input closer to the base condition or the terminating condition. So over here we are calling the same function with 1 plus 1, which is 2, and once we are inside the function again, n is not greater than 5, and we would be printing 2, and we would again call the same function with 3, which is 2 plus 1. So that's what we say function calling itself, which is recursion in simple terms. Okay, and again remember, a base condition is very important for any recursive solution, because if you don't have a base condition, you would have created an infinite loop, right? So you need the function calling itself to stop at some point, which is the base condition or the terminating condition. Now in this case, because we just want to print up to 5, if n becomes greater than 5, we can stop. So this is the base condition, and remember, if you don't have a base condition, you will get a stack overflow error, because computers don't have unlimited memory. Memory is limited, so you would get a stack overflow error if you have no base condition. So we have seen that recursion is just a function calling itself, which is what we have over here, until a base condition, which is what we have over here. So that's pretty much what recursion is in very simple terms. Now let's think of when to use recursion. If you have to solve a problem, and if you can see that the problem at hand can be divided into smaller subproblems, and if solving these subproblems can help you solve the original problem, then probably you should be using recursion. Now it's also many times the case that these smaller subproblems would be of similar nature, or they would be similar to the original problem at hand. Now what do I mean with that? let's take an example. Let's say you are given n and you want to find n factorial. Now, if your n is 5, 5 factorial is nothing but 5 into 4 into 3 up to 1. Or n factorial is just n into n minus 1 into n minus 2, etc. up to 1. Now, if you want to find n factorial and you're given n, or let's say for simplicity, let's say you want to find 5 factorial, okay, or let's say n is equal to 5 as an example, notice that if you can find the answer to a sub problem, let's say that's 4 factorial, again notice 4 is less than 5 and it's closer to the terminating condition or the base condition. So if you can find the answer to 4 factorial, you can find the answer to 5 factorial using the answer that you find, which is 4 factorial, because 5 factorial is equal to 5 into 4 factorial. And over here, 4 factorial is the subproblem, which is of similar nature to the original problem, and solving the subproblem helps us solve the original problem. So 4 factorial is 24. Now, using this 24, we can find the original problem's answer, which is 5 factorial, because 5 factorial is equal to 5 into 24. So if the question at hand has these type of characteristics, then probably you can solve it using recursion. Now, I know that this is a lot of theory, but we will do a lot of practice questions and this will become second nature to you. So don't worry about that. But again, let's take it step by step and let's proceed. So we have seen what recursion is, and we have seen from a high level when to use recursion. Now, let's take a look at the pseudocode of this, what we just now discussed over here for n factorial, to understand this in a better manner before we move ahead and try to visualize recursion. So if I were to write the pseudocode of what we just now discussed over here, let's say I have a function, you can call it factorial or anything to save space over here. I'm not writing any name for the function. And let's say we are calling the function with 5 because we want to find, let's say, 5 factorial. Now, inside the function, we have the base condition or the terminating condition that if n is equal to 1, just return 1. Because 5 factorial, as we discussed, is 5 into 4 into 3 into 2 into 1. And then notice after 1, you don't need to go further. So that's why if n is equal to 1, return just 1. And again, we will discuss as we go ahead in this lecture how you can systematically think of coming up with the base condition. But for now, because this is a very simple question, it's intuitive that if n is equal to 1, we can just return 1. So that's what you have seen over here. So that's the base condition that we have. And what would be the recursive case? The recursive case would be if n is not equal to 1, we just need to make the input smaller or call the function again recursively by having the input closer to the base condition or the terminating condition. So that would be return, we could just return function n minus 1 into n, right? So if you want to find factorial 5 factorial, we are just returning 4 factorial into n. So n in this case is 5. So we have seen that 5 factorial is 5 into 4 factorial. So to get this 4 factorial, we are recursively calling the function again with the input as n minus 1. And then to multiply this 5 over here, we have n into this part over here. So this over here is the recursive case. So whenever you think of a recursive solution, always try to think of the base case and the recursive case. So we have discussed some interesting things over here. Now in the next video, let's try to visualize this. Previously, we have discussed what recursion is and we have identified when to use recursion. Now in this video, let's discuss a powerful concept called recursive leap of faith. This concept will help us and understand recursion even better, and it also deals with how to actually go about using recursion in coding interview questions. Now, many times recursion feels like magic. If you're just able to wrap your head around the basics of recursion, you will see that you will be able to use this powerfully in solving a variety of coding interview questions, and that's why many people think of recursion, like feel of it as if it's magic. Now, what are the steps in using recursion? So the 5 steps in using recursion are these 5 steps over here, and let's go through them one by one. The first step is to understand the problem at hand. Let's take an example. Let's say you're asked to print a sequence that looks like this. So you have 3, 2, 1, 1, 2, 3. Now this is just an example. Let's say you are given n and you need to print n, n minus 1, etc. up to 1, and then you have 1, 2, etc. up to n. So that's what is over here, just for n equal to 3. The second step is to identify a subproblem. We have seen that recursion is suitable when you are able to break the original problem into subproblems, and solving the subproblems helps you to solve the original problem. So the second step over here is to identify a subproblem. Now, identifying a subproblem will become more intuitive, and you will be able to do it more and more easier with more exposure to a wide variety of coding interview questions, which we will take care of in this course. We will go through a variety of questions in the future sections, but let's take it one step at a time. So for this example over here, what would be the subproblem? The subproblem would be to print 2, 1, 1 and 2, right? So again, if you had to do this like 5, 4, 3, 2, 1, 1, 2, 3, 4, 5. Notice that the subproblem for the original problem is to print 4, 3, 2, 1, 1, 2, 3, 4. And the subproblem of this would be to print 3, 2, 1, 1, 2, 3, etc. Alright, so that's the second problem, which is second step, which is to identify the subproblem. The third step is the step of trust or faith, which is what we call the recursive leap of faith, and this is actually what makes recursion feel like magic, or this is actually what makes recursion so powerful and so helpful in a wide variety of coding interview questions. So let's try to understand this step over here. Now, the step of trust or faith is that you have to trust that this recursive call, which is like if we replace solving the subproblem over here with a recursive call, we have to trust that this recursive call will correctly solve a smaller version of your problem. Again, we will come back and try to understand this using the example at hand. So we have identified the problem, we have identified a subproblem, and we are saying in this step over here that if we replace solving the subproblem with a recursive call, we trust that if we have correctly designed the function, then this will be taken care by itself. So that is what this trust over here involves. Now, because we trust this, we don't need to mentally simulate or unroll the whole recursion, right? So this is the power of recursion. If you set it up correctly, and if you have the correct base case as well, then it's going to take care of all the other smaller subproblems without you having to unroll mentally all the various steps. So this makes recursion extremely powerful. Okay, so you assume your function works for simpler cases, it will work for more complex ones. So this is the step of the recursive leap of faith, which makes recursion, as we just now said, so powerful. Now, let's go through the remaining steps and then let's come back to this example again to understand this even better. Step number 4 is to link the original problem and the subproblem. Remember, in the previous video, we had said that recursion is useful when solving the subproblem is helpful in solving the original problem. So that's what we are doing over here. We are linking the subproblem to the original problem. So in this case, the original problem when n is equal to 3 is to print 3, 2, 1, 1, 2 and 3. Now, we have already taken care of 2, 1, 1, 2 because it's the sub problem, and we trust that the recursive call is gonna give us this output over here. Now linking 1 and 2 would mean to ensure that if you're getting this, just ensure that you're getting these parts as well in the output. Again, more of this in a moment. The final step over here is to ensure that you have the base condition correctly written out, because remember, for recursion you always need a base condition to avoid an infinite loop. Now in this case, for this example over here, let's say the base case is for 0, just return, because we just want to keep printing till 1. So for example over here, 5 4 3 2 1, and then when you reach 0, just return. We don't want to print it. All right, so let's say that's the base condition over here. Now of course you can write this in different ways, but let's just go with this for now. Now let's just make some space and revisit this problem over here. So, and let's go through the 5 steps again. So we wanted to print 3 2 1 1 2 3, and we identified that the sub problem is 2 1 1 2. We trust that if we set the recursive function correctly, if we write it correctly, then this over here is gonna be taken care by the recursive call. And then in step 4, we linked the sub problem and the main problem. That means we already have this part, and we just ensure that we get this also in the output for this example. And then we had the base case that for 0, return. Let's now go ahead and write the pseudocode for this. Let's say we call the function seek, okay? So seek for sequence, and we have the input n over here, and let's say we are giving 3 as the input. Now over here we are going to replace 2 1 1 2 with a recursive call to the same function, because remember, recursion is a function calling itself. So this over here is going to be written as seek with a smaller input. Over here we have n, so we're going to have an input closer to the base condition. Let's say that's n minus 1, because if n is 3, 2 is equal to n minus 1. And then in step 4, we linked the original problem and the sub problem. So we have to ensure that we get this and this 3 over here as well in the output. All right, and n is 3, right? So this is n in the original problem. So this over here, linking 1 and 2 in the pseudocode is gonna look like this. Print n, and then have the recursive call for n minus 1 to get this part over here, and then again print n to get this 3 also printed. So this is going to be the recursive case, and then finally we need to ensure that we have the base condition. So if n is equal to 0, we're just gonna return. So this is the base case, and this over here is the recursive case. Now this part over here is what we call the inductive step. In simple terms, induction, which is a maths concept, is that if this is gonna work for n, then it's gonna work for n minus 1, or it's the trust. All right, it's the trust part. If it's gonna work for n, it'll work for n minus 1 as well. So again, it'll work for n because we have set it up correctly, right? So we have printed n, so we got this 3 over here. Then we have done the recursive call to get this part over here, and we have done again print n to get this 3 over here. All right, so this over here is how we can apply recursion in a wide variety of problems, and again this will become more and more easy with a lot of practice. Let's take one more example over here. Let's say we want to find n factorial. Now quick side note, n factorial is just n into n minus 1 into n minus 2 up to 1. For example, 3 factorial is 3 into 2 into 1. Now notice that let's say n is equal to 5, we would want to find 5 factorial. Notice that 5 factorial actually can be solved as 5 into 4 factorial. Okay, so the second step, which is identify the subproblem, in this case would be 4 factorial. And it is the subproblem because if we know the value of 4 factorial, we can use it to solve the original problem, which is to find the value of 5 factorial. So 4 factorial is 4 into 3 into 2 into 1. Let's say you know the value of You know the value of 4 factorial as 24. Now you can use this 24 to find the value of 5 factorial, because 5 factorial is 5 into 24. Alright, so we trust that if we set this up correctly such that it works for 5 factorial, then it's going to work for 4 factorial, etc. Right? So that's our step number 3. And we're going to link 1 and 2, which is 5 factorial is equal to 5 into 4 factorial. Or in general terms, n factorial is going to be n into n minus 1 factorial. Notice this n minus 1 factorial is going to be a recursive call. Alright, so this 4 factorial, which is n minus 1 factorial, is going to be a recursive call. And we trust that it's just going to work magically. We don't need to mentally unroll it completely. Okay, and again, this over here is the inductive step. If it's working for n, and it's working for n because we have set it up correctly, that for n factorial, it's going to be n into n minus 1 factorial. So if it works for n, it will work for n minus 1. So that's induction. Again, it means that when we are trying to find n minus 1 factorial, this same thing over here is going to take care of it as n minus 1 into n minus 2 factorial. Okay, and this is going to work because we are correctly setting it up, and we are ensuring that there is a base condition. All right, so that's very important when you set it up. And the base condition over here, let's say, is if n is equal to 1, then just return 1, because notice over here we don't want to go further. Okay, so 5 factorial is 5 into 4 into 3 into 2 into 1. We don't want to go further, and we stop over here. So if n is equal to 1, then return. Now we will see in a future video how to make it very intuitive to identify the base condition. Basically, you can think of the base condition as the last valid input or the first invalid input, but more of that in a future video. So over here we have discussed the recursive leap of faith, which is what makes recursion so powerful and sometimes causes people to feel about recursion as if it is magic. Previously, we have discussed what recursion is, and we have developed some intuition on when to use recursion. Now, let's explore 2 powerful tools to visualize recursion. Remember, if you can visualize recursion for a coding interview question, it would be very easy to code out the solution. So let's explore these 2 techniques. The first technique over here is a recursion tree. And we have already discussed the question where we had to find n factorial. All right. And let's say we are just finding 5 factorial, and we have the pseudocode over here. Let's try to draw the recursion tree for this particular pseudocode. So initially, we are calling the function with the input 5. So let me just write f of 5 over here. And once we are inside the body of the function, because n is not equal to 1, it's 5, we will again call the function recursively. Over here we will call f of n minus 1, or in this case that would be f of 4. So let's write f of 4 over here. And once we are inside the function again for the input 4, we would again come over here and we would be calling f of 3, right? So again, that's over here, we would be over here, and we would have called f of 3. And in a similar manner, again, we would be inside the function with n equal to 3. N is not equal to 1, so we would come over here again, and we would call f of 2, right? And again, we would come over here, n is equal to 2, n is not equal to 1, so we will come over here, and we will call f of 1. Okay, now when we are inside the function with n as 1, because n is equal to 1, we have reached the base or terminating condition, and therefore we would return 1. So this call over here will return 1. So over here, when we called f of 2, we had to multiply this with n, which in this case is 2, right? So f of 2 will return this over here, which is 1, into n, which is 2 in that case. So f of 2 will return 2 into 1. Okay, and similarly f of 3 called f of 2, that's this part over here, for the call of f of 3, and then you have to multiply it with 3, right? So f of 3 will return 2 into 3, Okay, and similarly f of 4 will return this 6 over here multiplied with this 4. So that's 24, and f of 5 will return this 24 over here multiplied with 5, which is 120, or 24 into 5. So this over here is what we call the recursion tree. Now this is equal to 120 and we get the answer. Now you will see that in many questions the recursion tree will look something like this. You may have multiple branches. Okay, so again we will see that in the course as we go on to future questions, but I'm just mentioning it over here. So this also is a typical recursion tree that you will see. So if you are able to draw the recursion tree for a question, then you will see that as we practice more questions, if you can do this successfully, you will be easily be able to write the code for the solution, and this is in fact very helpful to identify the time and space complexity as well. Now more of that later in the course, but now let's proceed and take a look at another tool for visualization with respect to recursion, which is the recursion call stack. So we have seen the recursion tree. Now we are exploring the recursion call stack. So let's again take the same example over here where we wanted to find 5 factorial. So how would the recursion call stack look like? Now before we go ahead and visualize this, remember when a function is called, the computer allocates memory because it has to remember things like local variables, function parameters, return addresses, etc. So when a function is called, the computer has to allocate memory. So this is something that you should know. Now let's proceed and take a look at the recursion call stack for this question over here. So initially we are calling f of 5. So there would be f of 5 over here in the recursion call stack. Okay, so memory is allocated. Over here we have f of 5, and we have seen that f of 5 calls f of 4. So we have f of 4 over here, and at this point notice that f of 5 has not ended. That's why it's still over here, because notice over here we are returning f of 4 into n. So it would not have done the multiplication. This has gone to f of 4, and only once we get the value of this would the computer be able to do the multiplication of what we get over here with n, which is 5 in this case. So notice f of 5 has not ended. The computer has to hold on to it and remember it. So that's why we retain this over here. And then we proceed. F of 4 will call f of 3. That's something that we have seen. And then f of 3 will call f of 2. And then f of 2 will call f of 1. Now when we reach f of 1, we have seen that we have reached the base condition, so it returns 1. So this returning 1 over here, when this happens, it returns 1, and we pop out f of 1 from the recursive call stack. And again notice over here this follows the LIFO principle, or last in first out. Notice that in this call stack f of 1 was the last one to be added, and it's the first one to be popped out. So that's why we call it a popped out. So that's why we call it a recursion call stack, because a stack follows the LIFO principle, last in first out. Now again more of that later in the course where we discuss the stack data structure, but I'm just trying to link the concepts over here. Now this is the recursion call stack. Quickly summarizing, it's called a stack because it follows the LIFO, or last in first out principle. And again over here we have seen that when we called f of 5, it did call f of 4, and at that point f of 5 was not over, so the computer had to hold on to it. So popping out starts only when we start returning. So over here we have seen f of 1 was popped out and it returned 1. Now f of 2 can return because it got the value of f of 1 and it multiplies that value with 2. So f of 2 will return 1 into 2, okay, and we can pop out f of 2. Similarly f of 3 will return 2 into 3 and we can pop out f of 3, and similarly f of 4 will return 6 into 4, and we can pop out f of 4, and f of 5 will return 24 into 5, and we are done. We can pop out f of 5 as well, and we get the answer, which is 120. Now this over here is what we call the recursion call stack. Now the recursion tree and the recursion call stack are very powerful tools. They are very important because they help us to calculate especially the space complexity. We'll see that in future questions, and in many questions it's very helpful to calculate the time complexity as well. Now when we talk about the recursion call stack over here, we have seen that at max, at a point, it's taking up space of the order of n, where n in this case is 5. So over here, this takes up space of the order of n. So if we have a call stack that looks like this would take space of the order of n, which is again auxiliary space, it's extra space. We have understood how to go about visualizing recursion using a recursion tree or recursion call stack. In the next video, let's discuss the difference between recursion and iteration.